Okay, so our last notes today are on the counting principle. Remember, it's PLE, not PAL, like the principle, Mr. Pretz. It's the principle, the idea, and theoretical probability. So the counting principle, it's called the fundamental counting principle, and the theoretical probability. So this is just basic beginning probability information. So we have a problem. You are at the SOAR store, the spirit store, and have the following options for spiritware. So you're at the SOAR store, you're trying to buy a new Hawker Grove shirt, and these are your following options for spiritware. You have a t-shirt color, and you have red or black. You can pick the sleeve length, which is long or short. And you can pick the logo, which is a SOAR shirt, safe behavior, on task, act responsibly, respect self and others. You could pick an eagle shirt for our mascot, or you could pick a North shirt for our high school. So I'm going to pose the question to you. Let's figure out all of the different combinations of shirts you could buy. How many different shirts are there that you could purchase at the SOAR store? So to do this, we make a tree diagram. And a tree diagram is when you write out all the possible combinations. And a tree diagram kind of looks like when we factor, right? In elementary school, when you took the number 50 and you said, what can it be multiplied, or what are the factors of it? What times what equals 50? And you did 5 and 10. And you break down those numbers, right? Prime factorization. It's kind of like that. But instead of numbers, we're using words. And instead of starting with the answer, we start with the problem, and we work backwards from there. So I'm going to start with my first choice, which is t-shirt color. So I'm going to put red, and I'm going to put black. You have two choices for t-shirt color. Then if I choose a red shirt, I have choices of long sleeves or short sleeves. And black, I can do the same thing. I can have a long sleeved shirt or a short sleeved shirt. Right, so that's number 2. So step number 1, idea number 1, shirt color. Idea number 2, sleeve length. Now I'm going to go on to idea number 3, which is my logo. So if I choose a red long sleeve shirt, I can choose, and I'm going to abbreviate these because I'm going to run out of room on this third level because it gets pretty big. I'm going to put SOAR for S for SOAR. I'm going to put an E for Eagles, and I'm going to put an N for North. So red long-sleeved SOAR shirt, or a red long-sleeved Eagle shirt, or a red long-sleeved North shirt. Then I can go to my red short-sleeved SOAR shirt, or my red short-sleeved Eagles, or red short-sleeved North. go to black. Black, long-sleeved soar, black, long eagles, black, long north. Black, short, soar, black, short, eagles, black, short, north. And that's my tree diagram. So the purpose of a tree diagram is to list out all the possible combinations. So now I ask, how many combinations are possible? So when we look at how many combinations are possible, what we do is we add or count the bottom row. So if I look at my bottom row, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 possible t-shirt combinations at the Soar store. Now this is a lot of work to figure out how many combinations there are. The reason you do a tree diagram is because maybe it wants to know, like, you to list all of the possible combinations. And if it wants you to list all of the possible combinations, or it says draw a tree diagram showing all the different possible combinations, you're going to make a tree diagram. But if it just asks you the simple question, how many combinations are possible, you're going to use this idea called the fundamental counting principle. And again, it's PLE because it's an idea, not PAL, it's not a person. And the fundamental counting principle says this: if there are X ways to make number 1, so number 1, there were 2 ways. Y ways to make choice 2, and our choice 2 was 2. Z ways to make number 3, and we had 3 ways, and so on. You know, what if there was a 4th choice, and the 4th choice was, cotton or polyester? We'd add 2 more choices. So if there's X ways to make number 1, Y ways to make number 2, Z ways to make number 3, and again, these variables just represent numbers. You could use any variables. The answer, or what you do, is you do X times Y times Z. And if there was a 4th one, you'd multiply that one, and it equals your total. So if we look at this problem, how many combinations were there for shirt size or shirt color? 2. Sleeve length? 2. And logo? 3. So in our example, we did 2 times 2 times 3. 2 times 2 is 4, and 4 times 3 is 12. So it works. So if it asks you just the possible combinations, this is all you do. You multiply choice 1, choice 2, and choice 3, 4, 5, however many, and you get your answer. So this is used to find your total, because in theoretical probability, which is the theory behind the probability, not necessarily what happens, but if I just said, Mrs. Smith, who runs our source store, just give me a shirt, any shirt. I don't care. I mean, I really hope that it's a long-sleeved black shirt, but I'll take my chances. Theoretical probability is what we want over the total number. So if I was going to ask you what's the probability, and we say P for probability, and then inside I put black, long-sleeved, and I close it off, BL, meaning black, long-sleeved shirt, what's the probability? Well, let's look. How many black long sleeve shirts are there? There's 1, there's 2, and there's 3. You can have a black long sleeved Soar shirt, a black long sleeved Eagle shirt, or a black long sleeved North shirt. So that's why the tree diagram is important, because we can see all of the combinations. So I know what we want. I have a possibility of 3 out of, there are a total of 12 shirts. So my probability is 3 out of 12. Always simplify if you can. So instead of saying 3 out of 12, I'm going to say there's a 1 in 4 chance that Mrs. Smith will give me a black long-sleeved shirt at random.